So, dear students, good morning. Let us start with today this continue with this multiplication algorithms. Okay. Now, before that, let us go for the basics. Uh, so, in multiplication, first you should know that. So, if you want to multiply two numbers, so again in the multiplication there are two algorithms here, right? So, multiplication there are two algorithms. So, first algorithm is called shift and add method. Okay. So, shift and add method. Okay. Second algorithm is called Booth multiplier. Okay. Booth's algorithm. So these are the two algorithms which you are going to see in this video, which we are going to cover this shift and add method. In the next video we will cover this Booth algorithm. Okay. So, shift and add method when the data is represented in sign magnitude form, we will see this, right. So, when the data is represented in sign magnitude form, we will see how to perform multiplication using shift and add method. Similarly, when the data is represented in 2's complement form, we will see how to perform multiplication using Booth algorithm. So, these are the two algorithms. So, before proceeding with the algorithm, let us see the basics of this multiplication. So, first thing you have to understand is, if you want to multiply two n bit numbers, n bit into n bit, the result will be 2 n bit. The result will be 2 n bit numbers, right. So, this is the first thing you have to understand. Let me take example, that is, for example, if you want to multiply 5 bit into 5 bit, the result you are going to get is a 10 bit number, right. So, in this one number is called, right, as per the terminology, one number is called multiplicand. Okay. So, another number is called multiplier, right. So, first we will see the what is the, to understand this in a better way, first let us see what is the pen paper method which we follow in order to do the multiplication, then we go for the shift and add method. Okay. First, for example, you want to multiply these two numbers 23 into 19, right. So, you know that this result will be 437. So, I want to represent this with 23 with 5 bit. Okay. So, for example, 23 is represented as 10111, right. So, then 19 is represented as 10011. Now, I want to multiply these two numbers using the traditional pen paper method, right. So, this is called multiplicand and this is called multiplier. Okay. Now, what we look into this, so if the multiplier is 1, right, so we start with examining the multiplier bit. If the multiplier bit is 1, then what we do, 1 into we'll do this multiplication, what we'll get, 10111, right. So, next in this is the first step. In the next iteration, what we do, again we monitor this multiplier bit, this first we monitor this, now we monitor this bit, since it is 1, then again 1 multiply by this. Now, what we do, we shift left one time and we will write, right. So, 11101, right. Similarly, now similarly, since again we monitor the multiplier bit 0, since it is 0, so we will write all zeros, right. So, since again it is 0, so 0 into something is 0, so we will write all zeros, 0 0 0. Similarly, since again it is 1, right. So, again we shift left and right, 11101. So, yes, then what we do, so basically according this are all called the partial products, right. These are called the partial products, right. Now, finally, we will add all these partial products to get the result, right. So, if you do this 1, okay, so 1 plus 1 0, okay, 1 1 1 1 1 1 1 1 again 0 1 1 1 1 1 1 1 1 1 1 1 1 1 0 1, right, 1 1. So, 1 1 0 1 1 0 1 0 1. So, this is 1 2 3 4 5 6 7 8 9, this is nothing but 10 bits. So, this is nothing but 10 bits. Okay, so of course if I put 0, I'll get 10-bit result. So this is the final product which I'm going to get. Okay, so this is the 10-bit result. Okay, so here so finally what we are trying to do is, I'm trying to multiply these two numbers. Okay, I'll get the final product after after adding all these partial products. I'm going to get this final product. Okay, so now the point is the same. This is the traditional pen paper method which we follow, but in a reality if you want to implement the same thing in the hardware, we try to put little changes to this. We'll try to do little changes to this method. So what we do is, see, first thing we do is, so first observe here, if I want to store all this, so here we get 5 partial products, right? If I want to store 5 partial product and add at the end, I require a 5 registers, and I require a complicated ALU to add all this, right? So instead of that, what we do is, the first modification we do is, so whenever we get a partial product, we add then and there, like what we get. So for example, I get this, right? So 1 0 1 1 1, then I get 1 1 1 0 1. So whenever I get these two partial products, then I add there itself. So 1 0 1 1 1 0 1, right? 1 1 sorry 0 1 right? So 0 1 0 1. So whenever I get two partial products, I add as is, I add then and there and get a one more partial product. So this is the first change I will do. So rather than accumulating all the partial products and add at the end, I will add the partial products then and there. This is the first thing I will do. The second thing is, so what I am trying to do, whenever the multiplier is 1, I am writing the multiplicand here, and every time I am shifting left the multiplier. So instead of shifting left the multiplicand and right, so I will shift the partial product right. So that is the second modification I will do. So instead of shifting left to the multiplier and right every time, I will shift right. So instead of shifting left this and right, so I will shift right this, whatever the partial product in this case, I will shift right on this. So what I am telling is what we are trying to do. So right, so 1 0 1 1 1, I will shift left and right. So 1 1 1 0 1. So shift left, instead of this shift left, I will fix this, I will fix this, I will fix this, and I will shift right the partial product. So whatever the partial product, this will be shift right and this will be fixed. Multiplicand will be fixed, and right, partial product will be shifting, I will be shifting right. This is another change I will do, right? Also one more thing you see here. So whenever the multiplier is 0, so whenever the multiplier is 0, so 0 plus something is 0, right? So no need to perform addition, right? So that is only shifting is enough, right? So that is a third thing I am going to do, right? So these three changes I am going to adopt for hardware, right? So let us see what is the hardware required. So this is the hardware which I am going to use for the multiplication. Okay, so this is the hardware which I am going to use for the multiplication. So in this hardware, this is the hardware which I am going to use for the multiplication. In this hardware, you know that, right? So A register, Q register. So A register is initialized with 0. So initially A register, whatever the A register is there, so this A register is initialized with zeros, right? So accordingly, the same example I will tell how to do the same example. Like for example, I want to multiply these two numbers, right? 1 0 1 1 1 into 1 0 0 1 1. Here this 1 0 1 1 1 is the multiplicand, right? And okay, 1 0 0 1 is the multiplier. This is what we assumed in our example. So for this example, let me tell you how to do in this hardware the same example, right? So first of all, so this whatever the multiplier value, this multiplier value I'll initialize in the Q register, right? So 1 0 0 1 1 I'll put in the Q register. So A register I'll initialize with zeros, 0 0, right? Here I am assuming 5 bit, so all registers I am assuming it as 5 bit. Similarly, multiplicand I will fix to B register, so B register I will initialize with 0 1 1 1, right? Then I require every time so every time I want to shift, right? So I can shift with I can shift this, perform shifting in these registers. So you know that finally I am going to get the 10 bit result, so I require A register and Q register, 2 registers for holding the result, right? So what I need to do, every time I want to monitor this multiplier bit, right? So this bit first I will monitor, then I will monitor this bit, right? This bit, right? Right? So this bit I call it as Qn, right? So every time this bit, this may be 1 or 0 every time. So this bit I am calling it as Qn, right? So this bit I am calling it as Qn. So sequence counter is nothing but this is a register which is holding the count, so the count value of how many times I am going to repeat. In this case 5. So why 5? So number of bits is 5 in the multiplier. So this sequence counter is initialized with 5. So every time I want to shift right this, shift right, every time shift right this and perform addition with this parallel adder. So why I require complementer? In this case we are not using, of course in the Booth multiplier which we are going to use the complementer. So in this algorithm, shift and add method we are not going to use complementer, we are going to use this parallel adder, okay. Now also the signs, right? So A sign is stored in AS, B sign is stored in BS. So finally the result sign will be stored in both for example I can store in QS or I can store in both AS and QS. So how to get a sign again? See, if the both numbers are negative, it's a positive, both numbers are positive, it's a positive, negative, positive, positive, negative, it's negative. So how I know that? Using XOR gate, similar way how we do for identifying the comparing the bit, similar way I can compare the signs using the XOR gate and determine the sign of the result. So this is what the hardware, I hope you understood this hardware, right? So what I am telling is, so initially this multiplicand you want to put in the multiplier you initialize in the Q register, A is initialized with 0, so B is initialized with a multiplicand. Then sequence counter is initialized with how many times we need to repeat this process, and complementer and adder we perform this addition, so we can perform shift, right? Shift with this micro operation, shift micro operation in this EAQ, right? So let us go to the algorithm. So what is the algorithm? So this is a simple algorithm for performing this shift and add method. So first as I told that multiplicand in B, multiplier in Q, right? Then we perform, first we estimate the sign of the result. So of course the sign of the result is stored in both AS and QS. So you know that if we QS XOR PS we get the sign, right? If both are 0 or both are 1, so QS equal to 0, BS equal to 0, or since if both are positive, right? Both are equal to 1, both are negative. In both these cases we are giving this to XOR gate and deciding that the sign is positive 0. Similarly, if QS is 0 1 or 1 0, in this case the result is negative, means 1, right? So that's why using XOR this is how we using XOR gate we are estimating the sign of the result, right? So I am storing the sign of the result in both AS and QS. The final multiplier magnitude will be stored in both A and Q. This is what I told, right? So A and Q will be storing the result, and the sign of the result is stored in both AS and QS both, right? Now what we do every time? Every time, just to see here. So we monitor the Qn bit, that is the Qn bit represents every time it represents the multiplier bit, right? Every time Qn bit in every iteration Qn, y means we are shifting right every time, right? So every time Qn represents the multiplier bit which we are going to monitor. So this bit, right? So every time what we are doing here, we are monitoring this bit, right? Multiplier bit. So first we monitor this bit, right? So after one time right shift, this will come here. So this will become Q1. So every time this, just we need to monitor this LSB bit, right? So that I am representing here. So that Q1 bit, this bit I want to monitor Q1 bit. So if Q1 bit is 0, so if Qn bit is 0, just perform right shift, right? So right shift of EAQ, right? So be careful. So we need to shift EAQ both. We need to also consider the carry for shifting. So we need to perform this EAQ, total shift EAQ, right? Then, right, if Qn is 1, then what? So if Qn is 1, just we need to add and shift, right? So this is what the case. So Qn is 1 means what is the case? This is the second case. For example, in first case Qn this is 1, so we will add and shift, right. Then since Qn is 0 means this is the case, right. This case no need to perform addition, that is what I told, just it is enough to perform shifting, right. So it is a simple algorithm. So we will always monitor the Qn bit. If Qn bit is 1, perform addition and shifting, right shifting, right. If Qn is 0, perform only shifting, no need to perform addition. And what we do, we decrement the counter, right. So we repeat this process until the sequence counter not equal to 0. Once the sequence counter equal to 0, we will end this algorithm, okay. So this is the thing. So this example I will okay, the same example I will solve using this method. So whatever the method I told now, let me solve this with the method, okay. So what is the thing? So for example, first thing is B. So in the B register I have a multiplicand fixed 1 0, same example 1 1 1. So E A Q, I told that E is 0, A will be 0 0 0 0 0. So Q is initialized with the multiplier 1 0 0 1 1, then the sequence counter, right. So sequence counter first initialize is 5, 5 means 1 0 1, right. Now what we do, the first iteration, right, let us go for the first iteration. So first iteration what we do, so in every iteration just I want to monitor this Qn bit, right. I want to monitor this Qn bit since the Qn is 1. So Qn is 1, what I need to do, I need to add and shift, right. So what I need to add, I need to add this one, right. So to this I need to add this, right, add the multiplicand, right. So this can 1 0 1 1 1, right. Once I add, right, 1 1 1 0 1 0 E 0, Q will be 1 0 0 1 1, right. Now and this is the add, then I need to perform right shift, okay, right shift of what, EAQ, I need to perform EAQ. So EAQ means this bit will come here, so finally this bit will be going, right, go out. So now perform right shift, what happens, 0 will come here, so this 0 will come here, so 1 0, this 1 1, this 1 will come here, 1 0 0 1, this 1 will be vanished, right. This is what, this is the partial product, the first partial product, this is what the first partial product, right, the first partial product. Also SC will be decremented, right. So SC will become 1 0 0, so here it is 5, now 5 become 4, this is for the first iteration, right. Similarly do the second iteration. In the second iteration what again the you need to monitor the Qn bit, right, you need to monitor the Qn bit. Since again the Qn bit is 1, what decision I need to take, I need to do this addition, right. So what addition, 0 1, so here the partial product is 0 1 0 1 1. For this I need to add the, so this is E 0, I need to add the multiplicand, right, 1 0, okay, 1 1 1, okay. So 0 1 1 1 0 1 0 1, okay, 0 1, this is the multiplicand. So this is as it is, right, once we perform 0 0 1, then this addition is over. Now I need to perform the shift, right, shift operation. What is shift operation? If I do shift, what, 0 will come here, right, 1 0 0 0 1 will come, this 0 will come, this 1 1 0 0, right, 1 0 0 1 0 1 1 0 0, yes, yeah, this is the second iteration is well. So similarly sequence counter will become 0 1 1, right, it will become 3, right. So second iteration is over. Now let us go for the third iteration. In third iteration what is the case? Third iteration, just you observe here, this is 0, so 0 means what, just we need to do the shifting, right. So just do the shifting, what to do, so what I get, okay, let me draw with this red pen itself. So 0 0 1, right, if you do just shifting this, right, partial product, so 0 0 0 1 0 1 1 0, right. So this is the third iteration. Similarly, this will become 2, 0, 1, 0. This become 2, right? So 0, 0, 1, 0, 0, 0, 1, 0, 1, 1, 0. Similarly, again it is 0. So this is the third iteration. Again it is 0 means in the fourth iteration what in again just shifting. So what again shifting? So 0, 0, 0, 1, 0, 0, 0, 1, 0, 1, 1, right? So 0, 0, 0, 1, 0, 0, 0, 1, 0, 1, 1, right? Again this will become 0, 0, 1, it will become 1, right? So again it is 1. So 1 means again what? So let me write in the other page the partial product. So 0, 0, 0, 1, 0, 0, 0, 1, 0, 1, 1, right? So let me write here the partial product we obtained in the last case, right? In the fourth iteration we obtained E bit is 0. So 0, 0, 1, 0, 0, this is what, right? 0, 1, 0, 1, 1, this is what we obtained. Now it is 1 again. So 1 means in the fifth, so this count is 0, 0, 1, this is 1, right? So in the fifth iteration what I need to do, just take this 0, 0, 1, 0, 0 and add with the multiplicand. What is the multiplicand? 1, 0, 1, 1, 1, right? So 1, 1, so 0, 1, 1, 1, this is 0, right? So 0, 0, 1, 0, 0, 1, 0, 1, 1, 1, 1, 1, 0, 1, 1, 1, right? 1, 1, 0, yeah, 1, 1, 0, 1, 0, 1, 1, right? This is the addition result. Then we need to also do the shifting, right? We need to also do the shifting. So what is shifting? So this is 0. So this 0 will come here. This 1, 1, 0, 1, 1, 0, 1, 0, 1. So finally this is the result, right? Check out this 0, 1. So finally this is the result. So count becomes 0. So I can stop this process, right? So this is there in the AQ. So this 5 bits store in the A, this 5 bits store in the B. So this is the final product, right? 0, 1, 1, 0, 1, right? 1, 0, 1, 0, 1. So let us check with this result, right? 0, 1, 1, 0, 1, 1, 0, 1, 0, 1. So this is the final product, okay? So this is the first method, Babu, for solving. So in the exam point of view, you should know this hardware, right? You should know this hardware, you should know the algorithm, as well as you should know how to solve like this. If they give any data, you should know, in a iteration wise, you should able to solve this problem, right? So thank you very much.